Okay, recording started. Let's share the screen. Okay, good morning. Today's topic will be about the wiring and grounding problems, which is considered one of the major power quality things or power quality problems. So the thing when the customer complains about the power quality, most people immediately blame the utility or claim that the voltage is bad or the electrical company is bad. But in the field, especially in low voltage facilities like homes, shops, factories, many issues are not coming from the outside or they are not from the utility, not from the power company, but they are born inside the building because of the wiring and grounding problems. So today's lecture is not about the making about the power quality. Power quality was last lecture, but we were focusing more on the basic things that make the electrical installation safe, quiet, like regarding to the connection, bonding, grounding, and neutral management. In Jordan, the low voltage distribution, low voltage is 230 volts as an RMS or 400 volts RMS. But if like you, depending on three phase or single phase, so 230 volts for a single phase, 400 volts RMS for three phase, 50 hertz. So it is important that like to study about the grounding because there's, I mean, the thing which is related to the neutral, there is a lot of grounding and neutral problems, and they are, or they can be worse with modern loads, especially like with LED drivers, phone chargers, variable frequency drive, UPS systems like uninterruptible power supply, and IT equipments like computers, PLC, etc. These devices are everywhere right now, but they don't behave like the ohmic resistors or ohmic ohms, or I would say like Ohm's law does not apply on these because those are kind of nonlinear loads. So our goal today is to know, or like when someone tell you I have noise in the output voltage or I have noise in my home, for example, or in the electronic sector, you need to know that these problems can be from the grounding, especially like when if somebody says like I get shock from the power cabinet or my breakers circuit breaker trips randomly for no reason, or the PLC um, again, the things that you need to ask yourself, which is basically, is there a grounding or is it missing grounding? Is there a neutral to ground connection? Or so the thing, there can be many problems like ground loops. This is one of the common problems that we see nowadays. And sometimes like the neutral undersize or the neutral is very how to fix it. That that's the thing, which is what's the right decision to fix the problem. So here, like the agenda, typical wiring problem, missing ground connections, multiple ground connections, the ground loops, neutral sizing, standard solutions. Then the thing which is we need to imagine as an engineer that we've been called in the site to diagnose the problem, because we are engineers, as we know, we are a problem solvers. So the they called you, we have a problem on site. Now you are on the site. So the thing is not to start measuring the THD and reports, writing reports and say, okay, here's the reports, we have a bad THD, then the problem comes from the utility side. The thing, before doing that, you need to start by looking at the protection, like earth. Is the protective earth continuous? Is the neutral bonded incorrectly somewhere? Is there multiple ground roads creating different or different grounds, like this ground different than the other ground, different than the other grounds? Especially when we have multiple grounds, make sure that they are all almost the same condition. Like, are the other communications or computers or electronics between the equipments, they have different grounds, or are all of them sharing the same ground? And the other thing, which is the neutral, is the neutral heated because of the harmonics? This is not, I mean, we're not talking about something academic like here's a case study and do the other thing, but it is just a daily problem that we see in facilities. Like, it's not only in Jordan, but it can be worldwide. So especially whereas expansions are done over years, because initially when we build up the power system network in that shop or in that building or in that commercial area, it was in a certain load. Then after that, over the years, the loads can be different, or different contractors can work, or some new technologies can be inserted into the power, small distribution power system, then, or into the shops or the commercial areas, whatever we have, or the home. Then those will be added without understanding the system. So without being studied. This can make some problems in the power quality. So the thing, 80% of power quality issues are related to wiring, grounding inside the facility. So NEC, or basically the thing here about the reason, again, like a huge portion or 80% of the power quality problems comes from inside the facility, inside the building, or at the customer end, not at the utility end. So again, that's why we say, like, don't blame the utility every time, because the reason, I would say, like, again, 80% of the power quality comes from inside the power, inside the loads. So again, like NEC, which is National Electric Code, we need to make sure they are according to these standards. So let's think about it. If the utility voltage were bad, were truly bad, then the whole neighborhood will complain, not only your home or not only your commercial building, but usually complaints are located. One building, one floor, one room, one factory line, one server room. This is a big clue. So the thing here, that's the thing that you need to keep in your mind, which is if there is only one room complaining or one building complaining or one customer complaining while the rest of the customers are not, then you can think about the problem can be from the customer end, not from the utility side. However, if you have multiple complaints in the same line, then you can say, okay, this can be from the utility end, not from the customer end. That's the thing that you need to think about. If one customer make a complaint, then the first thing you need to keep in mind, is there a problem inside the customer facility or not? Now, about the standards, here we mentioned about the NEC or National Electric Code that have a minimum requirements. Even in Jordan, we are following IEC standards. However, in other countries, like for example, United States, they are following, can be something related to IEC and NEC. But here again, in Jordan, we are following IEC standards. But by the way, whatever they are, IEC or NEC, both of them, they have the concept is universal, which is there are a specific or minimum requirements for safety. And the power quality, and the sensitive electronics, sometimes they require the power, it can go beyond the minimum, or if we go better than the minimum, it will be better, of course, but we need to make sure it will not be lower than the minimum requirements. So our mindset is the code compliance keeps you safe from fire and shocks. That's the first reason. The other thing, good grounding and wiring practice keeps your equipment stable and quiet. So the thing which is we need to make sure that everything we are in safe area, nothing it will I mean safe. You will not be shot. There will not be no fire, not electricity. We want to maintain a good. Basically, we don't want for example, like the PLC or the computers or the electronic equipment to be restarted for no reason, or we don't want the circuit breaker to be tripped for no reason. That's the thing that we need to think about. We have fundamental IEEE Directory Standards 100, IEEE Green Book Standards 142, National Electric Code NEC, and some definitions. So the thing here, when those are major differences that can be used in industrial and to ground the system, and the pros and the cons, different grounding approaches. So the other thing, which is we need to focus on powering and grounding sensitive electronics equipments that give the best practice, and especially we don't want to make any problems. So if you want to be actually a real based definitions, standard evidence. So the thing that you need to worry about, let's say, I think it is like this, or I think it's like this. It's not the situation. And the thing is just you have some measurements or look at the problem, try to analyze it, look at some evidence, try to look for the like grounding, customer end problems. Then after that, look at these standards, make sure that you are familiar with the definitions of the standards, then see if these measured values are complies with the standards, or is there any contradict with them. That's the thing that we need to worry about. So why we are grounding? What's the reason for grounding? Two reasons. The first thing, personal safety, and the other thing, protective device operation. Then for personal safety, we want to prevent dangerous touch voltages if there's a fault energized on metal enclosure, or we want to make sure this fault will go to the earth. We don't want to, for example, like if there's a fault going on, 230 faults are waiting you or someone to shake his hand. This will create a problem, which will impact the overall safety, or it can make some fires. So that's the thing that we need to worry about. We need to make sure nothing will be impacted. Then let's talk like in many sites, like you can see it in Jordan, you might see earth road installed, especially in distribution homes. So people think that's enough to have the earth road installed there. But if bonding is poor, the earth path impedance will be high, then the fault currents might be too low to trip fast, so the dangerous condition can be in. Therefore, the grounding is not a decoration. It's not to say, okay, I just put a ground and that's it, so just put it there without a protective system or protection system. Then we need to make sure the grounding is being installed according to the standards without any big problems. Then, like typical wiring and grounding problems, here is like some specific problems, like problem observed, possible cause. This is basically the troubleshooting cheat sheet. So this can be your cheat sheet when you're doing any troubleshoot. Then you can see like burnt smell at the panel. When you smell a burnt at the panel or at the junction box or load equipments, then possible cause is basically related to the faulted conductor, poor connection, arcing, or overloaded wiring. The other thing, which is panel or junction box, is warm to touch. This is basically seems that high resistance connection or overload circuits. Then the other thing, buzzing or corona at low voltage side. Then buzzing is often arcing or loss in neutral. If the neutral there is a loss on it, you will hear that buzzing. or you see like corona happens basically more in medium and high voltage concepts, and they are basically buzzing. Like again, corona effects can be happening at the conductors in medium and high voltage concepts. You can see like the blue light around the conductors, while the buzzing, it's only in low voltage panels, and it is a red alert, which is there is some loose in the neutral or there's something going on in the board. It is basically either overload connection heating may fire starts exactly this way. So, or many fires starts from the scorched insulation. It can happen because of the heating and the overloading as well. So intermediate voltage at load equipments, this is a classic loose neutral or loose phase connection. It can make intermediate voltage at the equipment and intermittent interrupts. So you can waste days blaming the utility while the real problem is inside your junction box because there's some loose in the phase or some loose in the neutral. So I once saw a whole building complaining about bad electricity. The utility was fine. The real issue was the neutral bar screw was losing. So under that a specific load, the neutral floated and the voltage jumped between the circuits. Fixing one screw solved the entire building. So if there's a loose in the neutral or loose in one of the phases, it can create a big problem, which is something that we don't want. Okay, so there is a lot of, lists that can, for typical wiring and grounding problems. So the thing missing safety, or the first thing missing safety ground. So you will see two wires outlets or green wire cuts or metal trunking not bonded. The system can be shocked or equipment's noise or breaker not tripping during the faults because missing safety in the ground, which is it will not detect there is a fault. The other thing, multiple neutral to ground connections. So this is extremely common in buildings where they're making expansions. When someone connects neutral to earth for a sub panel, thinking it's improving the ground. So multiple grounding roads, but this actually creates parallel return path and can cause trips or like can cause like a grounding loops as well. So underground equipments, so metal enclosure, cable trays, rack, and even water pumps, if they are not bonded fine, they can just flow. Then additional grounding roads, people think more roads means safety, but it's not always true. If roads are not bonded properly into one grounding electrode system, you can create different earth potentials, which is basically creates multiple grounds, and these multiple grounds means different voltage potential, which will make the currents to flow between the two grounds. So grounding loops, especially, it can happen in IT and in rooms basically related to the computers, networks, communication networks. This become noisy, making the poor communication, random resets, noise in the data, which will make a create problems. And the other thing, insufficient neutral, the modern building, they are, we have, basically the vast majority of the neutral is good, or in the neutral is. However, in the old days or old buildings, then you can see like the neutral wire is very thin. So basically what's happening there, since it's very thin, we have some harmonics, it comes from electronics, which is called the tripling harmonics, or it's called the third harmonics. It can be significant value, so huge currents can flow in there, while this small thickness of neutral make it incapable of handling that big or that huge value of neutral current comes from the triplet harmonics, which create a problem and make it overheat. So missing ground connection. So here, like, it's about life or death. So by looking through the diagram, if the load has an internal fault, phase conductor touches the metal cabinets. If the cabinet is poorly bonded to protective earth, fault current shoots through the power electronic, the power conductor, then back to the source and trips the protection quickly. But if the protective earth is missing or broken, what happens? The cabinet becomes energized, sitting at line potential. The breaker might not trip because of the protection earth does not exist. It will not detect the trip. So the fault current's path is weak, maybe through the dust, moisture, or a person. Then when somebody gets shocked, or there is a fault because of the dust or the moisture, then you will be shocked that circuit breaker will not trip. Then this is how many people get killed because the electricity is not tripping, or the circuit breaker is not tripping, which is called missing bonding. So in older buildings or small workshops, you will find machines with earth pin removed, or extension cords with no earth continuity. This is exactly the problem. So the ground rod alone does not guarantee a fast trip, but the protective earth conductor and bonding are what create the low impedance return path. So again, some people just say, like, let's put the grounding rod or the ground rod alone and it's just sufficient, but no, just make sure the protective earth is working properly. The other thing, which is multiple ground connections, which is only one neutral to ground connections at service entrance, because there are only neutral to ground bond in the system. Typically at the entrance or the main bonding points, downstream panels should keep neutral and protective earth separate. So here we need to make sure that the intent of common grounding practice and also reflected the National Electric Code principles. Because if you bond neutral to ground multiple places, the neutral returns current splits, which make part of the returns on the neutral through the neutral conductor and part through the protective earth system, or to the cable trays or the building steels. This means you can have currents on things that should never carry currents in normal operation, like grounding systems. Or in other words, this can create a problem or create a current into the ground, which is something that we don't want or something undesired. So touching voltage on metal parts will be very dangerous because there is a ground current on the ground, or it can create some strange noise problems, or it can make some other challenges. So in many low voltage installations, RCDs are used in homes, offices. Multiple neutral to ground bonds can cause continuous leakage current path and lead to random RCD trips people. Then bypassing the RCD, which creates a safety hazards. So understanding this will prevent a very real bad practice. Ground loops. So the imagine two devices like a PLC panel and motor drive panel is grounded at different points. Because grounding connected conductors have impedance, then the two grounds are not exactly equal to each other. This creates a potential difference or a voltage difference. This potential difference somewhere during the faults can make conduction. So when there's which is called the potential difference, this makes a current to flow, a path to the current to flow. So now connect these two devices with a copper a communication cable, the shield or preference conductor attached to the ground together, and circulating currents flow into the loop. That circulating current or circulating currents can make a ground, something we call a ground loop. That ground loop can make communication errors, random resets, corrupted data, or that there's a problem in the data. What that we don't want. It can impact the cameras in the building, the Ethernet cable, the other things. So this can create a big problem. And the other thing, which is neutral sizing. Neutral sizing, tripling harmonics. The thing here, third harmonics can be additive to the neutral. The third harmonics comes from, again, from the electronics or from like switch mode supplies, again, based on power electronics equipment. And this can add up to 170% of the fundamental frequency phase currents, which is 1.7 times the fundamental. This is something dangerous. Then basically, in modern low voltage, if a balanced three-phase system at the fundamental frequency, phases currents will cancel each other at the neutral, which makes a zero neutral. This is the classical story that we already know. But with many modern loads, when we have like power electronic supplies like computers, electronics, LED drivers, variable frequency drives, etc., the current waveform are not pure sinusoidal. It contains a harmonics. The key is the third harmonics, or we call it triplet harmonics. Triplet harmonics is not only the third harmonics, it can be multiple three. It can be third harmonics, ninth harmonics, 15th harmonics, etc. Those are called triplet harmonics. Again, triplet harmonics is not only about third, it can be third, ninth, 15th, etc. Multiple of three. So here's the dangerous part. The triplet harmonics are in phase with all of the three phases. So instead of canceling the neutral, they can be added to the neutral. I mean, instead of being cancelled in phase A, phase B, phase C, the harmonics, all of them can be additive. You can add all of them together. So this why it makes the neutral not canceling them. They will be added. So the harmonics, third harmonics on phase A are in phase with phase harmonics of phase B, in phase with third harmonics of phase C. Then at the neutral, there will be three times the third harmonics. So that's why the neutral currents become a very high, even if the phase currents are balanced, or even if the load is balanced. But the problem is about the load, because the load can create a triplet harmonics because of the power electronics that can create up to 170% of the phase currents worse than what we have in the load. So when you go to any office buildings, whatever, if you are in Amman, Erbil, wherever you are, so many PCs, monitors, phone chargers, LED lighting, they are based on power electronics. So if the installation was designed like an old building, or if you're an old building design with small and neutral, we can get something like some challenges like neutral heating, melted insulation, burnt neutral power connection, voltage unbalance between single phase circuits, complaints of equipment failure. Sometimes computers can be reset for no reason. However, in modern buildings, we don't size the neutral as that. So we were studying like the load harmonics, so the neutral size will be bigger, then it can handle this triplet harmonics. That's the difference between the modern buildings and the old design buildings. So standards and solutions. The thing here, like we shift from what goes wrong to how to do it right. So let's look at this diagram map of the correct installation. Look at the transformer provides the supply. At the building service, you might see like you have the main bonding jumper that bonds the grounding conductor or the neutral to the grounding electrodes system at one point. The downstream panels distribute phase and neutral, and the grounding conductor bonds enclosure and equipments. So the key separate rule, or the idea, make neutral carries normal return currents. Protective earth carries fault currents only. That's the thing that we need to think about or to focus on. Equipments enclosure are bonding so that we don't have a floats. Then make sure that the grounding system is not supposed to carry currents in normal operation. That's the key, or that's the goal, or the golden thing. The grounding system is not supposed to carry currents in normal operation. If you see the currents in the ground at no fault conditions, then there should be a problem. Then the problem is the grounding thing. Okay, standards and solutions. So let's go deeper. Grounding is not a magical zero ohm points. So the grounding electrodes has a resistance and impedance. The resistance of the conductor to the road and the road to soil contact, there's a resistance, and the soil resistivity itself. So all of them can contribute. So we need to worry about these to make sure those are according to the standards, then their impact will not be too high. The other thing, during the faults or lightning strike, the large current can flow into the ground system. Voltage equals to the current times impedance, which make the whole facility ground can rise potential or temporarily, or we call it spike, a very high voltage spike. This is called ground potential rise, or GRP, I'm sorry, GPR, ground potential rise, GPR. So soil resistivity can be high in many areas, especially in the dry or rocky soil. This means ground electrodes resistance can be higher than the expected unless the design properly or has been designed to be something different. Then we need to pay attention to electrode design, not just install one rod and leave. So at lightning in winter season, it can create transients on grounding potential rise or GPR and can cause equipment upsets, especially in rural feeders. Also, there's some need to worry about the service entrance. Is the single reference points? That's the thing that we need to worry about. The service entrance is the single reference point to the ground. This is the only point that we connected it to the ground. Then we need to make sure underground water pipes, only if it is metallic and continuous and legally allowed. Building steels, excellence for the grounding if properly bonded, very low impedance. Grounding rings, a conductor ring around the building, create reducing resistance and equalization potential. Concretes in case electrode. So it's very effective because concrete retains moisture and provides a good contact. And the end, we can also can be as an electrode options, which is a grounding rod. This is very common, but performance depending on the soil and how heavy it is. So in modern installation, we prefer to combine electrodes into one bonding grounding electrode system. Don't create separate islanded of grounds. That's the thing. Isolated grounds. So we need to make sure, look at the sensitive equipments. So an isolated ground does not mean no connection on Earth. It means you provide dedication insulated grounding conductor for sensitive receptacles so that the noisy current from other equipments don't share the same ground path. In data rooms, like in labs, medical equipment rooms, whatever, you might see devices are extremely sensitive to small voltage differentiate and noise. Then if there is a problem on other devices in the same equipments or in the same network, this can impact the medical devices or the data room devices or the labs that we have because some ground loops can go on. Therefore, an isolated grounds oftenly make the life difference, or it can help by isolating the ground, and they will not see a problem. So it can face a controlled grounding path back to the server reference. Then isolated ground is not a magic to fix bad wiring, but it is a technique is used when the bonding is already correct, the neutral ground separation is correct, and you want to remove or you want to remove the extra noise that you have. Then if someone uses isolated ground to hide a bigger problem, they are hiding the building problem or making a building trouble. But the thing here, we are using this as a protective devices for sensitive equipments. That's the thing. Separately derived facilities. So a separately derived systems means you intentionally create a new source, often via isolation transformer with a delta Y transformer. So the delta side can block certain harmonics and zero sequence currents. The Y side provides a new neutral and new grounding reference at the secondary. then you can bond neutral to ground at the secondary as appropriate for the derived systems. Then this can reduce noise and can help in sensitive loads, for example, hospitals, telecommunication sites, large IT rooms, data rooms, industrial control systems. But again, you must design it correctly. The grounding and bonding of separately derived systems is a specialized topic. We cannot cover it in one lecture, but the key message here is sometimes the best way to protect sensitive equipment is to redefine the local reference rather than fighting noise on the same conductor. Okay, so from service transformer, main bonding at service entrance, feeder, panel, then isolation transformer, creating the separately derived system. Then you can say like you are creating a clean island for sensitive loads, but you still must bond all metallic parts and ensure fault current path exists. A clean island is not floating island, but it is controlled. That's the thing that you need to keep in mind. Grounding for signal references is very important because it breaks a common misunderstanding. Engineers often think grounding is only about 50 hertz, but for noise switching transients, harmonics, we care about high frequency behavior. So the grounded conductor can have low resistance at DC or 50 hertz, but high frequency inductance dominates, where that means the impedance rises with the frequency. Look at like the graph. So the here, like for example, like the green wire is only ground, or the ground wire has high impedance, peaks at megahertz range, which meaning it's poor performance for small signals. When you add a small signal reference grid like a mesh bonding network, you lower your impedance across a wide band. In buildings with lots of variable frequency drives, inverters, UPS systems, you have switching frequencies and fast edges that creates high frequency noises. If grounding is long and thin, the noise cannot return cleanly, it spread and cause interfaces. So the signal grounding, we want low impedance across frequency, not just low resistance. Okay, so at high frequencies, conductors behave like transmission lines. The rule of thumb shown here, when a grounded conductor is longer than about 1/20 of the wavelength, means it stops behaving like a simple short connection. So a long ground wire from a sensitive device to a remote ground point might actually be useless, or the ground can be useless for high frequency noise. The device ground bounces and can get errors. So if you have a control cabinet and a drive cabinet connected to a long grounded conductor noise, it can still, or we can see noise can still appear. But we need to make sure, like to consider local bonding, wide copper straps, mesh ground plan, short connections. This is why electromagnetic compatibility engineers, we call them EMC engineers, love wide straps because it has a lower inductance. Then we need to make sure the conductor, the ground conductor is longer than 1/20th of the wavelength because again, here we are considering this as a transmission line. Okay, grounding of sensitive equipments. Basically, individual branch circuits for sensitive equipments, we don't mix noisy loads and sensitive loads on the same circuit. Puts server and PLC control power on clean circuits, while like we need to make sure the conducts should never be at the sole grounding patch because a quantity connection or poor connection can loosen, corrode, or be painted. So with dust and humidity variation, relying only on conduct continuity is risky. The other thing, which is green wire ground, same size as current carrying conductors, that's we need to worry about because during faults, ground conductors must carry fault currents safely without a problem until the protection operates. That's the thing. We need to make sure that the neutral should carry a high things. That's how we can think about. The other thing, if poorly bonded, like buildings steel can provide excellent low impedance grounding. Then we need to make sure good grounding is not on one road. It's about network of bonds that keeps everything at nearly the same potential. Then here, we need to make sure that about summary firing and grounding solutions, no current should flow in the grounding under normal conditions. This is a golden statement. If you measure currents on powered earthing, we need to make sure, there is no current. If there is a current, there is something wrong happening, which is basically multiple neutral to ground bonds um, can happen. Equipotential reference, all devices should share nearly the same reference potential. This reduces noises and prevent risk shocks. And bond all metallic housing, so never leave a metal floating. A floating metal eventually become energized. Only one neutral to ground bond. Basically, this prevents parallel returns path and keeps, which is keep the protection or for the earth protection clean. Grounding, bonding standard repeatedly emphasize controlling where system grounding is applied, which is the thing. The other thing, enough interconnects. It's not only about the 50 hertz or the DC components, but it's related to the frequency with higher frequency. A good ground panel is a low impedance network, not a single wire. Then you need to worry about like it is not a single wire, it can be a network like or as a transmission line. So we need to make sure like tightening and re-terminating neutrals, or we need to make sure to make the power factor or the power quality good or to reduce them. We can solve them by tightening or re-terminating the neutrals. That's one of the things that you need to worry about. Removing illegal neutral to ground links in subpanels, bonding cables, trays, and racks correctly, upgrading neutral sizing in offices full of electronics, improving the grounding electrode system with boarding electrodes and building steels. Many solutions are not expensive. Just make sure do the correct engineering. Just tightening a losing screw can solve a big problem. Okay, so the thing which is when we think about the grounding, like the language of all devices that agree, this is the right zero. This is the zero that we need, or this is the zero that we will consider. So if your building has 5 different zeros, then the zero, if you different than the zero of the other room, the zero of your other neighbor, and so on, which will create a floating zero. That's something we don't want. So your devices will argue which ground is the right correct ground. Then the argument appears as a noise, resets, trips, and sometimes shocks. So your job as a power quality engineer is to make sure the building speaks one grounding language, only one ground. Multiple grounds creates a problem. Okay, so this is the end of today's lecture. Let me stop recording.